Hi everybody, our project title is Multilingual Auto Lipsync Dubbing for Video Calls. Our team members are Gautam R, Gautam Balaji and myself Dhanushwardhan. Our project guide is Dr. Shobha S. Abstract of our project is to use advanced ML technologies to enhance video call experience. In our project, we have built a cascaded wave-to-lip model that translates and dubs the language from sender side to the preferred language of the receiver side along with proper lip sync. So the objective of our project is to build a cascaded wave-to-lip model and to translate synthesis speech into audio and to synchronize lip movements for the languages spoken by the user and to build a WebSocket T-Inter interface. So the tools required are a WebSocket T-Inter interface, Google Audio to Speech Converter API, Google Translator API, a wave-to-lip based AI model, and Python to train the model. Over to Gautam R.
So first I'll be explaining the steps involved in our project. Obtain the input video and the user's preferred language for translation, and then separate the audio and video and store them in a chunk folder. Convert the audio to text. Translate the converted text to the user's preferred language, and then we convert the translated text back to audio format. Meanwhile, check the duration of both the audio and video, and if it aligns and align the audio with the corresponding video time span. And then finally apply the wave-to-lip model to synchronize the lip movements with the audio. Next slide. So next I'm going to talk to you about the literature survey of our project. So the first paper introduces a novel method for dubbing educational videos from one language to another. This aims to enhance the comprehension for all students. It employs an LSTM model to predict and encode lip landmarks, generating lip regions over time. So these lip regions are integrated into the video using a unit architecture and then synchronize them with the dubbed audio. Unlike conventional methods, the faces are generated and synchronized in real time, resulting in a seamless viewing experience for students. Next paper. So next, the paper introduces an LPIPS attention wave-to-lip, which is a method for creating realistic talking head videos synced with audio. This employs a unit architecture with a convolutional block attention module, which is CBAM, for enhanced informatic fusion. And then the semantic alignment modules ensure feature alignment, while LPIPS loss aids stable training for quality lip sync. The evaluation includes visual quality, assessed by inception distance (FID), and lip sync accuracy using LSCC and LSED metrics. So the training utilizes mainly 3 datasets and prioritizes stability with LPIPS loss, aiming for efficient production of accurate lip sync videos. Next one. So the next slide, the research tackles the issue of unnatural audio-visual experiences in translated and dubbed videos, aiming to cater to a global audience. By incorporating embedding attention mechanisms and SSIM as a loss function, this proposed system achieves superior accuracy and visual quality in speech-to-lip synthesis across 3 datasets. It introduces innovative techniques to enhance lip movement synchronization, resulting in an improved viewing experience for online viewers worldwide. Next slide. So this paper introduces a conditional generative adversarial network, which is JAN, for lip sync, serving as an alternative to the wave-to-lip model. So the process involves separating processing of audio and video, which are then synchronized to produce translated videos. Audio translation employs automatic speech recognition and translation models, while video translation involves face detection and lip generation. So word-level processing uses SSML tags and hi-fi JAN work order aid in audio translation. Although this model is slightly less efficient compared to the wave-to-lip, it achieves comparable lip sync error descents, LSED and LSCC, results on the LSAT2 dataset. Next. So next I'll be explaining to you the methodology involved in our project. First is the audio processing. So the audio is extracted in real time using Google Speech Recognition API to obtain an accurate transcript. High quality microphones are recommended to ensure minimal errors. Translation and conversion to audio. The extracted transcript is translated using Google Translator into the desired language. It is then converted back to audio using the GTTS Python library to ensure accurate noise-free input for the proposed model. Next slide. So the process audio along with the video is used to generate lip sync videos. The proposed system supports multiple languages and utilizes cascaded wave-to-lip for synchronization. It extracts features from audio and video, integrates them, and then generates lip movements and updates the model based on law synchronized video and output. Next. So this would facilitate seamless audio dubbing and visual lip sync synchronization, as explained in this slide, in the web interface, enhancing user engagement across different languages. Our proposed system facilitates the process of audio dubbing as well as visual lip synchronization. Using a vast combination of certain libraries in our proposed video call web interface is ensured, thereby enhancing the users to have natural engagement in the session with their fellow speakers across their desired linguistic choice. So a large dataset of video clips are coupled with various audio files. The dataset is then meticulously processed to extract the frames of audio features along with the frames. Wave-to-lip framework comprises of mainly 2 phases, such as lip region extractor and lip sync generator. The accurate identification and extraction of the lip-centric points of each and every frame of the video is a prominent function of the lip region extractor. Now, after successful extraction of lip-centric regions, and the lip sync generator comes to play, where it makes use of the processed audio to be transformed into spectrograms, capturing the frequency spectrums as well as the temporal nuances with the help of Mel frequency septal coefficients (MFCCs), which has to be utilized to generate synchronized lip regions frame by frame. Next one. So this is the spectrogram equation of the audio signal A tau and can be computed as given below. Frame after frame, the retrieved lip syncs are cropped and aligned for further analysis. The training step combines supervised learning and adversarial training to ensure the realism in our lip synchronization. The combined supervised learning and adversarial training goes through layers of processes, which includes the whole model in training. The loss function L can be defined as given below and is a combination of supervised and adversarial loss. L supervised denotes the supervised loss, L adversarial denotes the adversarial loss, and lambda is the hyperparameter, and it controls the balance between these two terms. Utilizing gradient descent optimization, the model parameters theta are updated iteratively as given below in this equation, and mu represents the learning rate. So after the completion of the trained data, the process model generates the lip synchronized frames, which is explained in this diagram. So basically, the approach represented in the above figure generates high quality lip synchronized dub videos in real time as a result of our cascaded wave to lip model, which is wave to lip plus wave to lip, and it utilizes the data frame by frame alongside each block of our wave to lip model. Here, the lip synchronized video from the first model serves as input for the second model in order to obtain our final lip synchronized video output, which could have a much more efficient output in the end. Next. So the final post-processing steps make sure that the receiver gets the perfect resultant video. So why we opted for this cascaded model is because the subsequent loading of the resultant lip synchronized video makes the lip synchronized better and efficient. So here the audio input is the same throughout loading for both the models, but in order to attach the lip synchronization more stronger and convincing to the visual data. So more subsequent cascading of the wave to lip models might not be recommended since the consequent attaching of lip regions may make the processing time much worse comparatively. And hence we have opted for the cascading of two wave to lip models to analyze the merits of using such a model in a real-time application. The next slides will be explained by Gautam Balaji.
So the main aspect of our project is all our model must be processed and the input must be retrieved. Everything must be done altogether in real time. And for that, we have developed a video call web interface using tkinter in Python. So with this web interface, users can connect and communicate with each other in real time, ensuring that they could opt for any three languages which we have provided option as of now: English, Tamil, and Hindi. And the user can have the privilege of sender and receiver as two roles. And when the user has the option to speak out, they should make sure they use the sender privilege. And during the other time, the user must have the receiver access. Next page. Next. So these are the three main aspects in real-time data processing. The first one is data acquisition. In real time, the user must give his or her own video input along with the audio through his or her own device, webcam, and microphone. And the second one is audio processing. The extracted audio must be converted to the text form using the Google Speech Recognition API, and that extracted text must be translated into the receiver desired language using Google Translator API. And this translated text must be converted back to into the audio form to the same receiver preferred language. And the third aspect is data transmission and synchronization. After the model displays the output, final lip synchronized output, this output video must be transmitted in real time to the receiver side. Next slide. And these are the technologies we have used for our web interface. First, model. The model must be trained in such a way that it retrieves the input from the user and transmits the video back to the receiver simultaneously in real time. And for receiving the video input, we have used OpenCV. And for receiving the audio input separately, we have used PyAudio. And the Google Speech Recognition API is used for recognizing the audio spoken by the sender and generate words in the sender's input language. And the translation of the text is done using the Google Trans library. And this translated text must be converted back into the audio form, and that is done by the Google Text-to-Speech (GTDS) library in Python. And finally, the audio length, the processed audio length, the translated audio length must be matched with the video length so that our web model generates effective results. And for this, we have utilized the Lebrosa. Next slide. So here are the two basic functionalities of our website: front-end web interface and back-end server. And for the front-end web interface, we have used tkinter in Python, which creates a proper video called UI. And for the back-end, we have used the sockets with which users can communicate with each other and connect together through our video called web interface. Next slide. So coming back to results and comparison, we have done a lot of research and we have analyzed many metrics with respect to existing models. So first we have displayed the graph where we have calculated SSIM scores, Lipsync error, LSET and LSEC scores with respect to three languages: English, Tamil, and Hindi, which we have given option for. And if you see, the SSIM scores are maximum for our model, which is wave to lip plus wave to lip, and even the LSET and LSEC show better results in case of our model. Next slide. And we have also analyzed the mean opinion score. For this, we have created a survey where 10 to 15 members were asked to fill out, give us the ratings for our model with respect to dubbing as well as the lip synchronization. And even for this, we have inferred that our model has the highest MOS score, which is 4.6 with the accurate precision of 0.06. Next slide. And this is the comparative study which we have done with respect to previous existing papers and also with our own data sets for different models. And from this, we can infer that the SSIM, PSNR are maximum for our model. SSIM is 0.97, which shows that our model works efficiently with producing high quality results. Next slide. And so from all this results and comparison, we have concluded that our model will deliver quality outputs with respect to lip synchronization as well as audio dubbing in real time. And this we have analyzed also two extra scenarios to check how well our proposed system works. Let's see that. Next slide. So the first scenario we have taken is when the face is being at static position, which is straight into the camera, and when the face is when the face moves on continuously. And even for this, we have there's no much difference between the two cases, but still our model works very efficiently for the face at rest position. Next slide.
And the other scenario which we have taken is the one with the illuminated background, well lit condition, and the one with the dim background. And even for this, even for both the cases, our model works efficiently. But the illuminated background gives us little bit extra quality results compared to the dim background. So we opt for our model working in well lit condition always to get efficient results. Next slide. So now let's look on to the video call web interface which we have developed. I will explain each and every functionality of our website in the let's see one by one. Next slide. So let's look into the first salient features of our web page. First, socket connectivity. How many users are joining together? Each and every user must be connected to each other through socket connectivity, and real-time dubbing will be done with whatever the user chooses the language, and the lip sync part will be handled over by our cascaded web model. And we have altogether created this user-friendly interface where the cascaded web model is being integrated with. And as I said earlier, the user can have two roles: one is sender and one is receiver, according to their wish. Next slide. So this is how the sender page will look like, which we have differentiated color-wise. And the green color shows for sender side. So once the user joins the video call session, he will once he chooses the sender role, he will see this page. Next slide. And to differentiate between the sender and receiver, we have used blue color for the receiver side. In this picture, we have taken the scenario as two receivers. One can opt for one language and another can opt for any other language, with which accordingly he will get the output result and video in real time. Next slide. So this is the exact page where the sender will start recording his own video and as well as the audio, and you can clearly see the UI shows like recording the video, and the receiver is also connected. Next slide. So after the sender records his video, he can check whether his video is correct or how efficient his quality and everything can be checked with the preview of the video below at the bottom of the page. Next slide. So after the sender stops recording the video, this video will be processed in real time using our cascaded web model, and all the audio and video qualities must be checked, and it will be fed to the cascaded web model, and it will deliver the processed video with the dubbing as well as the lip synchronization. And as I said earlier, in this case there are two receivers. One can opt for maybe Tamil and one can opt for Hindi, and in real time the two receivers will also be getting two different languages output in the same time simultaneously in real time, so that so they can see the processed video at the bottom of their page in the receiver side. Next slide. Yeah, so that's all about our video call web interface and as our whole proposed system. Now, after that, Dhanush will take on to explain about the working of the video call web interface.
Let's see the demo part of our project. We have two scenarios. Let's see one by one. In this scenario, we have one sender and two receiver. So the content from the sender will be converted to two different languages along with the lip sync and will be received on the receiver end simultaneously. And I will attach the lip sync output along with this video. Hello, how are you? Hello, how are you?
नमस्ते आप कैसे हैं
வணக்கம் எப்படி இருக்கிறாய்
नमस्ते आप कैसे हैं
Let's see the second scenario. In this scenario, we have one sender and one receiver. So the content from sender 1 will be converted to the language preferred by the receiver, and then the receiver's content will be converted to the language preferred by the sender along with lip sync. Hello, how are you? Hello, how are you?
வணக்கம் எப்படி இருக்கிறீர்கள்
நான் நலமாக இருக்கிறேன். நான் நலமாக இருக்கிறேன்.
I'm fine.